Hello friends. So, welcome to the lecture in which we will discuss Python implementation of singular value decomposition and how to implement low rank approximation in Python. Previous lectures we have already done the theoretical concepts of singular value decomposition and low rank approximation. So, this lecture is more towards how implement these concepts in Python. So, as you know that singular value decomposition can be considered as one of the most popular and widely used decomposition method. Decomposition in the sense matrix decomposition methods. Most of the data sets we obtain the covariance matrix, and then to decompose covariance matrix we use some decomposition technique. However, this covariance matrix is a very nice matrix, it is symmetric matrix which always have the eigen decomposition or spectral decomposition. But many other matrices related to data science and machine learning does not have this beautiful property of symmetricity or positive definiteness. So, there we use the concept of singular value decomposition. So, in this lecture we will learn a Python implementation of singular value decomposition, and then we will explore one of its application in image processing, where we will see various low rank approximation of a given image. So, just recall you the theoretical concept what is SVD. So, if you are having a m by n matrix A, the singular value decomposition of this matrix A is U into S into V transpose, where U and V are orthogonal matrices of size m by m and n by n respectively, whereas S is a m by n matrix, where it will be having a m by m matrix or n by n matrix depending on whether it is a flat matrix or thin matrix. Depend on this concept we will be having a m by m or n by n submatrix, diagonal submatrix in S. Okay. And then when we talk about reconstruction using SVD, so given U, S and V, you have to reconstruct your matrix A, and that is quite straightforward. You multiply U, S and V transpose. However, in case of reconstruction we are having truncated SVD also, where instead of using all the singular values we use a small subset of bigger singular values to have a compressed version of the matrix A, and that example I have already given you in low rank approximation. So, now let us learn how to implement it in Python. So, for implementing it in Python I will use again Google Colab, and here I have constructed this example to make this implementation clear. So, I will use again NumPy here. You can also use scikit for implementing the singular value decomposition sklearn, but I am using only NumPy. So, given a rectangular matrix A, it can be factored in the form of A equals to U sigma V transpose, and this is the singular value decomposition of A. Now, in very first cell and in very first line I am importing NumPy as NP. Then what I am doing? I am fixing some print options of NP array with precision 4. Then I will have a 3 by 4 matrix, and I will see the singular value decomposition of this matrix. So, the first row of my matrix is having elements 1, 2, 3, 4. So, as I told you in one of the previous lecture that when you are going to feed a 2 dimensional array or a matrix, you have to use np dot array, and then you can put your first row which is having element 1, 2, 3, 4. You can put second row having elements 1, 1, 2, 3, and the third row where elements are 0, 1, 1, 0. So, if you see if I run it, I can print it. So, you can see this 3 by 4 matrix 1, 2, 3, 4, 1, 1, 2, 3, 0, 1, 1, 0. Let me make a bigger size of the font. Okay. So, this is my 3 by 4 matrix. Now, I want to factorize this 3 by 4 matrix A as the product of U, S and V transpose, where U will be a 3 by 3 matrix, V transpose will be a 4 by 4 matrix, and this S will be having a 3 by 3 diagonal submatrix, and other entries will be 0, means fourth column will be a 0 column vector. Since the size of the matrix is 3 by 4, so the matrix A can have at most rank equals to 3, okay, at most 3, it may be 2, and as I told you in the previous lecture that the number of non-zero singular values equals to the rank of the matrix. So, now if this matrix A is having rank 2, then sigma 3 will be 0. If it is having rank 1, then sigma 2 will be 0, only sigma 1 will be non-zero, and if it is having full rank 3, then all sigma 1, sigma 2 and sigma 3 will be non-zero. So, now I will apply the singular value decomposition of this matrix A. So, for applying the singular value decomposition, you have to use this command np dot linear algebra. For linear algebra, you will put lin-alg. We have used it in one of previous lecture also, where we were calculating the eigenvalues and eigenvectors, and then dot SVD. So, this SVD functionality will give you the singular value decomposition of this matrix. So, here I am passing my matrix A, and then I am going for full singular value decomposition. So, if I run it, the singular value decomposition has been done. If you see your matrix U, so you can see it is a 3 by 3 matrix, and then if you want to see whether it is a orthogonal matrix or not, you can simply use the basic matrix algebra, the product of U and U transpose, because a matrix is orthogonal if U transpose equals to inverse of U. So, it means U into U transpose equals to identity matrix. So, let us check U dot U dot transpose, and you can see it is coming identity matrix. Okay. So, I am having matrix U which is a orthogonal matrix, and that can be verified by this command. Okay. Similarly, you can see the matrix VH, and then you can check. So, if I put matrix VH, it will be a 4 by 4 orthogonal matrix, and the matrix will be like this. In fact, they are orthonormal also. If you want to check it, again you use VH dot, means I am taking the product of VH and VH transpose. So, you can see it is a 4 by 4 identity matrix. Now, let us see what is this S in this singular value decomposition. So, this S is a one dimensional array containing the singular value of the matrix A. So, first singular value sigma 1 is 6.7509, the second singular value is 1.1734 and the third singular value is 0.2186. So, sigma 1, sigma 2 and sigma 3. Now, I told you that singular value decomposition is something like U sigma V transpose. So, now this one dimensional array S which you are having as an array of singular values, I will make a matrix sigma. So, the size of the matrix A is 3 by 4. So, the size of the sigma will be 3 by 4, where if you take the first 3 row means all 3 row and first 3 columns, that will be a 3 by 3 diagonal matrix, whereas the fourth column will be a 0 column. So, let me try to make it. So, for that I will use this command SD equals to NP dot diagonal S, and if I see what is SD here, I can print this SD. It will be a 3 by 3 diagonal matrix. You can see where diagonal elements are singular values. Now, to make it sigma, what I need to do? I need to add a column here, 0 column. So, let me do it. So, for that I define a 3 by 4 matrix B. You can see it is a 0 matrix. And now, what I will do? I will assign here that B, the first 3 columns of B will come from SD, which is a 3 by 3 diagonal matrix containing the singular values. So, these first 3 columns, first, second and third will be replaced by these 3 columns. So, that the fourth column will be 0. So, in that way I will be having my B, and here I will be having matrix sigma which is equals to B, and if I print sigma, you will be having this 3 by 4 matrix containing the singular values. Okay. So, now I am having my matrix U, I am having my matrix V and I am having sigma. Let us try to reconstruct back the matrix A. So, for that I need to multiply U with sigma and then V transpose. So, let me write sigma here. So, print NP dot. So, here this middle one will give you the product of U and sigma, and then the outer NP dot function will give you the product of U sigma with V transpose or VH. So, let me do it. So, after this I am having this matrix, and if you see, this is nothing your matrix A. So, now what I will do? Here you are having 3 singular values. If I go here 6.75, 1.17 and 0.21. So, the rank of matrix A is 3. Let me see the 2 rank approximation of this matrix A. So, as you know from the previous lectures that the 2 rank approximation can be done by making this singular value as 0. So, I will replace this singular value 0.2186 by 0 in my matrix sigma. Okay, so, for doing that, let me define my S again. So, I will define S as let me define it here. So, I am defining S equals to 6.7509, 1.1734, and the third one, this 0.2186 I will replace with 0. So, I have done it. So, now my SD will be having last column as 0 column, you can see, because now this singular value is 0. Now, I will define a matrix B of 0 matrix of size 3 by 4, and in this B I will copy the first 3 columns of the matrix SD. Yeah, and then I will write this B as sigma. So, here last 2 columns will be 0 columns. So, now the rank this will be having only 2 non-zero singular values. Now, let me reconstruct back a matrix which is a rank 2 approximation of matrix A. So, you can see this one. This matrix is a rank 2 approximation of the matrix A. If I print A also, so you can compare elements wise. Yeah. So, if you see, this is a 3 rank matrix, original matrix A, and it is a rank 2 approximation of matrix A. So, it is a low rank approximation of the matrix A. So, you can see the first entry is 1, here first entry is 1.0959, second entry is 2, it is 1.95. Okay. So, this is the best 2 rank approximation of the given matrix A, and in terms of the difference between these 2 matrices and taking their norm. So, you have learned it in theory lecture how to define the objective function for getting the low rank approximation. Okay. So, this we have done so far. So, originally we got this kind of singular values of A equals to 3 by 3 matrix U, sigma and V transpose. Another example you can see, because here we have seen a 3 by 4 matrix where number of rows are less than number of columns. You can see another example where number of rows are more than number of columns. So, for that I am modifying my matrix A. So, now A is a 5 by 4 matrix, number of rows are 5. So, now singular value decomposition of A will be U, which will be of size 5 by 5, sigma which will be of size 5 by 3, and V transpose. So, the same command I am using for singular value decomposition, that is np.lineage.svd of A, and you can see your matrix U, which is a 5 by 5 matrix. It is an orthogonal matrix. You can see S, which is a one dimensional array giving the singular values of the 5 by 4 matrix A, and here you can see the last singular value is 0. So, the rank of matrix A is 4 here, and this is 4 by 4 matrix VH. Okay. So, in that way you can perform singular value decomposition as well as low rank approximation of a given matrix in Python. So, this is my first exercise of this lecture. I will take one more application of this singular value decomposition, especially in image processing. So, let me open that application. Okay. So, what let us come to this application. So, it is a in this example I will perform a singular value decomposition of an image, and then I will check different low rank approximation of that image. I am importing NumPy, I am importing pandas which is for data, I am importing here CV2 for imaging kind of application. For displaying the image I am importing CV2 IMShow and other image functionality. Finally, I am also implementing I am importing matplotlib.pyplot. Okay. So, in first cell what I am doing? I am importing the utilities which I will use in this implementation. Now, what I will do? I will load an image from this URL, okay. And at this URL I have put an image. I will read that image as URL, and then I will read this URL as my img. So, this my img is a color image. So, a color image will be having means m number of rows and number of columns if it is of m by n image, and then it will be having 3 bands, red band, green band and blue band, that is RGB. So, it will be a 3-dimensional array. So, what I will do to make it 2-dimensional array equivalent to a matrix, I will convert it into a gray image. So, what I will do? I will add the corresponding pixel values from all 3 bands, and I will take the average, and that will be my gray image. So, this gray image is nothing, it is a matrix 2-dimensional array. Okay. I will read this image as img underscore mat, which is now my 2-dimensional matrix. I will print it, I will check the shape of this matrix, and I will also see what kind of image is this. So, let me run first utilities. Now, I am reading this image. Yeah. So, here you can see the size of this matrix is 720 by 960, means 720 number of rows and 960 number of columns. These are some of the entries of this matrix, and these are nothing just pixel values of a gray level image. It will be between 0 to 255, any integer value, 0 for pure black color and 255 for pure white color. And if you want to see this image, I have plotted it. Okay. So, I have plotted it, you can check it. So, this is the image. Now, what I will do before applying SVD, I will scale the entries of this 2-dimensional matrix which representing this image. So, what I will do? I will scale all these numbers such that mean will become 0 and standard deviation will become 1. So, what I will do? I will subtract mean from each entry and I will divide by the standard deviation. So, by subtracting mean from each entry of an array, mean will become 0, and if you divide the modified entries by the standard deviation, then the standard deviation will become 1. So, let me apply this one. Now, like the earlier example, I will perform the singular value decomposition. So, again I am having 3 matrix U, S and V. S is in fact a 1-dimensional array which will be having the singular values of this image. The same command np.lineage.svd, and here I am passing my scaled matrix, this one, after performing the scaling. Okay, so, I have done the singular value decomposition. Now, I will compute the variance explained by each singular vector. So, it will be having huge number of singular vectors, like size is 720 by 960. So, at least so it will be having more than 700 singular vectors. Okay. So, I will compute the variance, and it is very easy, you can compute using this formula, and then I will plot something like first 11 eigenvectors, or let me tell singular vectors, first 10 singular vectors, okay, and I will see the variance explained by those singular vectors. So, you can see this kind of plot. So, on the x axis I am having singular vector, whereas on the y axis I am having variance explained, and here you can see as we are going far away from means first singular vector is representing somewhere about the 60% of the variance, whereas second one is having something like more than 15% of variance. Similarly, third one is having more than 5% of variance, fourth one is having about 5% of variance, and then as we are going next we are having less variance. So, if you cut down the number of singular vectors, means instead of taking all 700 plus singular values, you take only first 10, 15 or 20 singular values and reconstruct your image using those. Then you can save lot of memory, lot of storage of to save this image. So, you will be having a compressed version of this image, and this is a beautiful application of singular value decomposition. Let me try to do that particular thing. So, first I am reconstructing using only 5 singular values. Please note there are 700 plus singular values. I am using only 5 singular values. So, you can see how what is the rate of the compression. So, you can see I am getting this image. So, it is not a very good quality image, but still I am able to make out some of the visual information of the image. So, let us go to 50 singular values. So, you can see this is the image which I am obtaining using 50 singular values, whereas the original image is having almost 700 plus singular values. So, you can see even I am taking very less number of singular values, out of 700 plus I am taking only 50, still I am getting a very good quality image, not like the original one. Certainly I will lose data, but still I am having a good approximation of the original image. This is the image using 100 singular values out of 700. So, I am using only 1 by 7 data of the original image. So, it is a compressed version, and you can see the quality is almost similar to the original one. This is when I am using 650 singular values. So, you can see the 100 singular values and 650 singular values, both of the images are almost same. Why? Because after 100 singular values are having very small value, very close to 0, they are not contributing much in the image. So, let me see all these together. Yeah, so here you can see using 5 singular values, using 50 singular values, using 100 singular values and using 650 singular values, and both of these are very good approximation of the original image. So, in that way we can compress our data using singular value decomposition, or in other way using the low rank approximation. Okay. So, in this lecture we have learned how to implement singular value decomposition in Python. We have seen one of the application of singular value decomposition in image compression using the concept of low rank approximation by cutting down a number of small singular values out of the list of the whole singular values. Similarly, you can use this kind of you can use this truncated SVD kind of thing to have a better version of your big data. We will explore more in future lectures, means we will explore more applications of SVD in our future lectures, where we will apply this concept of SVD and this truncated SVD especially in principal component analysis. So, with this let me close this lecture. Thank you very much.